All right, so I am going to do a little bit of a live coding experiment here today. And what I'm going to do is I'm going to code up a simple convolutional neural network for a very simple test environment. And I'm doing this to build neural networks. Going to do this with PyTorch, which is a very common API that makes building neural networks very easy. And I'm going to do this in Google's Colab notebook environment, which is basically a way of using um, Google's cloud computing. So basically allows you to set up a virtual machine on one of Google's in Google's cloud and use their GPUs and their computational resources to make everything kind of easier. I'm doing this because writing a neural network from scratch, even with PyTorch, can be very daunting. Um, but I also want to note that my goal is not to teach you what a neural network is, not to teach you deep learning, not to teach you how they work or how to train them or why they work. Really, the goal here is to kind of walk you through the process, and in particular, kind of walk you through some of the ways that I use the Jupyter notebook infrastructure that Colab uses to debug neural networks as I go along. And this is very much in contrast to kind of more conventional ways of programming in Python, where you might have an IDE where you kind of write your code in one file, save that file, and run it through the interpreter. What Jupyter notebooks and Colab notebooks allow you to do is basically write incrementally, which means you can also test incrementally and debug incrementally, so that once you have everything kind of together, you know it's all going to work. And then you don't have to kind of run everything and watch it all crash and kind of figure out what's going on. So this is going to be basically a process where I kind of take you through how I kind of use the environment to structure my thoughts and work my way through the APIs as I build a neural network. So with that kind of set up, let's just kind of jump in here. Okay, so we're going to build a neural network. You can see on the screen here, we have a Colab notebook. What we're going to do is we're going to build a simple neural network that is going to take some images that are produced by a particular program or an environment called minigrid. And well, let's just see it, right? So minigrid is something that you can get off of GitHub. It's a very simple kind of 2D game like structure. You have a little agent in red. Agent is trying to get to the green goal. There's some walls that they have to navigate around through the black is free space. And under some configurations of this, the agent has a certain amount of space that it's allowed to see. So basically, it is able to see everything in the gray squares in this gray box. So it has to use what it can see to make particular choices. So in this particular environment would be good for doing reinforcement learning. We're not really going to do reinforcement learning. We'll do something kind of inspired by it. We're going to say, given a box, a image, given to us as pixels, can we predict the highest, or predict which action the agent should take next, right? So if this agent is in this particular orientation in this particular spot and wants to get to the goal, it might want to go forward. It might want to turn to the right and go down because it's got to get through this slot here, right? So which of the actions it has available is the best choice it should make, right? So from pixels to a score for every particular action. Okay. And then if we train this neural network, it should be able to predict the right action and then execute that action. Now, we're not going to do all of the training loops. That can get very involved. What I'm going to do is mostly focusing on how we kind of design and write the neural network itself that takes the pixels and produces some sort of classifications or scores. Okay, so back to the notebook. The first important thing we should know about notebooks is basically once we have this loaded up, this is basically it basically sets up a virtual machine inside Google's cloud, right? So I have basically my own CPU available to me and a Python 3 environment. So if we connect to it, that's going to set up the virtual machine. I want to actually kind of make sure that we got the right kind of machine here. So I'm going to go and change the runtime environment. So I'm going to want a GPU. And so right now we don't have any hardware accelerator. We can switch this to a GPU. And when I rerun this, it's actually going to restart a new virtual machine. And this virtual machine is going to have a GPU. So we now have a virtual machine with a CPU and a GPU. And what's going on inside here is we have these things called cells where we can write code and we can execute the code. We can basically send it directly to the Python 3 interpreter and get the output back directly from the interpreter, right? So we can write our Python in here. We hit the go button. Basically, this is executing whatever code is in this box, and we produce whatever output we want from here. Okay, so that's of course not the important, interesting thing we want to do. And then the nice thing about this is we can actually kind of create more cells, and we can move back and forward and kind of write in a nonlinear sort of way, which you'll find to be particularly helpful. And I'll show you how this works. Okay, so now the first thing we're going to do is we're going to want to set up PyTorch, okay, because that's going to be the neural network API. And so there's a kind of a standard set of API that we are going to need here. We need to get PyTorch, which is called Torch here. The neural network tools. We use the torch dot neural network functional is basically an extra set of utilities if we should need it. I don't think we will need it, but we'll get that just in case. Oopsie. There's optimizers for training our neural network built into PyTorch, so we'll grab those. We're also going to use NumPy, which is a set of mathematical tools, very efficient, as well as array management. We're going to need that. And I don't know if we'll need this here, but I like to grab PDB, which is the Python debugger, which gives us the ability to set checkpoints if we need to do that. All right, so once I hit this button, we're actually going to load all those into our Python environment. So those are all available to us now. And if I want to keep writing code, I can just keep making new cells, and I can run those when I'm ready. Now, this next cell is going to be kind of special. I'll write it and I'll explain what's going on here. But you might kind of recognize this immediately. The pip install is what we use to install packages on our computers. This bang here, the exclamation mark basically says, get out of the Python environment to the shell, underlying shell environment, and run the code that you see to the side of it. All right, so it's basically going to say, all right, well, let's break out of Python. Let's do this pip install, get that, and then come back to the Python environment. And so we can see that it'll run as if it's running in the shell. It's going to download and set itself up pretty fast because this is a pretty small, very simple environment. And then, we're going to want to load that package. All right, so import gym minigrid. All right, so now that is available to us. So the first thing I want to do is I want to set up a little game so we can start to get some image data from that game. And I don't remember exactly how to do that. So I'm going to come back to the GitHub and I'm going to look at the instructions, and I can see here that there's a few things we want to do. We're going to import something called minigrid wrappers. So I happen to know that there's basically multiple ways of getting different types of data out of this environment, which are called environment wrappers. But then the key thing here is we're going to make a new environment. Gym is an API that allows us to hook neural networks up to environments, data generation environments, games, whatever, particularly easy. These are the wrappers in play. Basically, we're going to say, I want RGB images from our game. And minigrid gives you some additional information. And this basically says, throw out any additional information. We only want the pixels. Okay. And then once we do that, when we reset the environment, it'll give us our first observation. All right. So we're going to load that, and now we have an environment and we have our first observation. But before we get into the observations, I think it's really kind of helpful to see the game itself. So we're going to basically, I want to make it so I can see what the game looks like. Okay. I just like to know my data. I like to get to know my data, right? So what we're going to do is we need to create an image from the game. Now, fortunately, gym environments know how to render themselves. They can give us lots of different ways of giving us different information. I'm going to ask it for an array of RGB values, and I'm going to scale it so it's not too big, it's not too tiny. And I'm going to show that image inside the notebook. This is code for rendering it. And now what we see here is Colab's kind of nice. It actually tells me that there's an error. What's happening here is I'm asking to use a package that I have forgotten to load. So one of the nice things about notebooks are that if you make a mistake and you did something and you forgot something, you can just kind of go back and you can make a new cell. So what if I'm missing? Library that I'm going to use is called pyplot. I forgot to load that in, so I will get that loaded in. And now it's been loaded in, and I can go ahead and run this cell, and it has now rendered the game for me, right? Okay, so we see the agent, we see its goal, and again, the lighter shaded stuff is what the agent itself is able to see. So that is what is being given to us in this initial observation that we got. So the first observation when we set up the environment. Okay, so what is this observation, right? What is the agent giving us in terms of data from this game? Okay, so let's go look at this. Make another cell, and let's just ask it, what's in this observation? Well, there it is. It's a NumPy array. It looks like it's 3-dimensional, and it's a bunch of numbers. Holy crud, that's a whole bunch of numbers. All right, what's going on with these numbers? Well, let me see. Maybe it's actually not so important what the numbers are. Let's make a small change here. What shape is going to do is it's going to tell us what our dimensions are. So what this is telling us is that the observation is a 56 by 56 by 3-dimensional array. Okay, what is this? This is like the width of the screen in pixels, the height of the pixels, and 3 is the number of color channels, red, green, blue. Okay, so it's a 56 by 56 by 3 array, and we can look at it again, right? So these must be, this is probably a red, green, blue. So 146, 146, 146, that's probably a particular color of gray. Okay, so 76 by 76 by 76, that's a darker gray. Okay, so this is our screen data. Okay, we can verify that. All right, and again, it's a 56 by 56 by 3. But actually, there's a little bit of an issue here. So I want this to be I want to have color channels first, right? So I want this to be 3 by 56 by 56. So I want to have my red, green, blue as my first dimension, and then all my information after that. So in other words, this is not in the right format, right? It's not the right shape. So I'm going to have to make a little change. I'm going to make a new variable. I'm going to call it state. So this is going to be like the observation state. And I'm going to use some of the powers in NumPy to transpose my different dimensions. So what I'm doing here is I'm basically saying I want the third dimension first, the first dimension second, and the second dimension third. So if I do that, and I can actually print this out, and I'll even print out the shape here, right? So we can see we have changed the data. We haven't changed the data, right? We've reorganized the data, right? So now it's a 3 by 56 by 56. Okay, so what have I done here? Well, my color channels are first. So if I ask for what is my state 0, this is red. So these are all of the red channels in my data, right? All the red values for every single of my 56 by 56 pixels. Okay. And you can also see here, I can make changes to my cell, and I'm just rerunning the cell over and over and over again, so I can see my changes, so I can play with my data and get a good feel for my data. This is always kind of the first thing, is to get a feel for your data. Okay, so there's another issue, which is I would really wish that these numbers were not from 0 to 256, but I wish that they were from a number between 0 and 1 in terms of their red strength, their green strength, and their blue strength. So one fun thing we can do with NumPy is we can just take everything in our array and we can divide it by a particular value, like the max. And now suddenly we have fractional information. Okay. All right, so now we're getting this closer to the data that I think would be really useful for my neural network. Another thing we want to do is, well, the information is given me in NumPy. NumPy is a very kind of good intermediate representation, but PyTorch has its own array representations called tensors. So I need to be able to convert this to my torch tensors. And well, PyTorch knows how to do this already, so I will tell it to convert my state from a NumPy array into a PyTorch tensor. So if we do this again, now we see we have a tensor. It's still three-dimensional. It's still got the same values, but you can see that the type is now a tensor, and it is a 64-bit floating point. There is one last thing we want to do. I actually want it to be in a 32-bit floating point. So I'm going to do a typecast here. So that'll give me into a 32-bit float. Okay. And the other thing is that tensors don't use shape. They use the size function. So here we can actually see that we now have a tensor with the size 3 by 56 by 56. Okay. So that is great. That's exactly what we wanted to do to be able to get the piece of our data from an observation from our environment into the right form. Now, I'm not going to want to do this every single time, but what I've done is I've figured out basically how to convert my data to the right format. So if only I had wrapped this into a function. We'll call it prepare state. We'll give an observation, and these will be the set of steps we want to do. Of course, I don't need to print, but I do need to return the state. So what have I just did, right? So when I was playing with this cell and I was modifying it over and over again, kind of incrementally getting the data closer and closer to the format that I needed, I was basically writing a function, but I was able to run it kind of over and over and over again. Once I know it works, then I wrap the whole thing inside of a function, and now I have a function that I know is going to work. So let's just load that function into Python's memory, and it's ready to go for whenever we need. Okay, so before we go on, I'm going to do one more thing. I would like to visualize the observation, right? Shapes are important, but it might also kind of help if I know exactly what it looks like. So we're going to create an image from the array that contains observation. And there's a cool little package here that just takes any array information, treats it as RGB, and figures out how to make an image out of it, which we will show in the output of the cell. And again, I always forget to do this, right? I forgot to load the package that has image. It's from a package called pill, which is probably Python image library or something like that, right? All right, so let's kind of make sure that's loaded in here. Now we can run it, and we are missing something. I forgot to tell it to show the image, right? So again, if we get an error, right, we can just change the cell, fix it, rerun it. And here we go. So a little bit rasterized, but you can kind of see here, basically you have the agent, there's the triangle. Now this is egocentric vision. So this is from the agent's perspective. It's looking along the wall and it's seeing a wall in the distance. Okay, so you can compare that to the ground truth of what the game actually thinks is going on, which is the agent, is looking to the right. If we ask the agent, well, the agent's always looking forward, and forward just happens to be up. All right, but we can see what the agent now sees directly from the data that it has produced from in the game. Okay, so I feel like I'm a little bit comfortable with the data now. Let's go ahead and set up a neural network. Okay, so in PyTorch, to set up a neural network, we are going to create a new object. We'll just call it net because I'm not very creative. All neural network objects inherit from the neural network.module. So we're going to do that. And when we set up networks, there's basically two things you need to do to get these to be trainable. First is you need to set up the initializer. And what is the information we need to set up a neural network? Well, let me see. We probably need the height and the width and the number of actions, right? Because remember, we're going to take a screen of size, height, width, and we're going to produce a score for every single action. So our outputs are going to be some sort of an array of the size num action. Okay. We better call the super function constructor just in case something has to happen there. And let's remember how many actions we have in case we need it later. Okay. Num actions, I think that'll work a little bit better. Okay, so there's two things we need. We need the initializer, which will fill in, and we also need something called the forward function. So the forward function is the set of instructions on how to actually run data through the neural network. Oops. So in neural network parlance, we usually call the inputs X and the outputs Y. So let me see, I will say, more specifically, we often call it a Y hat. So hat means estimate, right? So what is the estimate of the output? And just for now, I'm going to kind of put this in here and say, I don't know what it is yet. Now, if I want this neural network to be trainable, I need to specify what are the different layers, and I wish I put inside the initializer. And then I say, how do you run your data through those layers, which is what goes into the forward function. Now, I could get into this and I could start writing, and I could write everything down, and I could try it, and I could see if it crashes, and I could try to figure out where it breaks and fix everything. But I'm going to, again, use the notebook to kind of allow me to debug as I code. I'm actually going to write the body of the neural network in some separate cells below here. But for the time being, I'm going to just kind of make myself some notes about what I want to have happen. Okay, and what I know is I'm going to have, I think I'm going to need 3 layers. And each of those layers are going to have several PyTorch modules. Okay, so on the first layer, we're going to do what's called a convolutional layer. So a convolution basically takes an array of pixels and kind of runs as a sliding window across all those pixels, looking for combinations of pixels or windows that create good estimations of the final output for the neural network. Okay, that's called a convolutional network. So I'm going to create a convolutional layer. It's going to start with 3 channels. So what are those channels? Is red, green, blue. Those are the raw features. And it's going to try to learn a number of features associated with the screens. And I don't know what good numbers here. I'm just going to kind of pick a number. I think 16 sounds like a reasonable number. And the other thing I need is a kernel size, which is basically how big the window is. And I don't know how big it should be, so I'm going to set it kind of small. I'm going to set it for 2. Right. Now, once I run it through a convolution, that's usually convolutions are followed by some sort of nonlinearity or activation function. I'm going to use a ReLU, a rectified linear unit, which is kind of one that has been shown to work pretty well with this kind of data. And then one thing that is often done, at least at the first layer, is we'll do a max pool. That's my first layer. My second layer will have another convolution. And this time we're going from 16 features or channels. And a nice thing to often do is to kind of grow the neural network, okay, to allow it to progressively find more and more features of relevance. So let's go from a 16 features to 32 features. What are these features? I have no idea. Basically, we're going to let the neural network figure out what the interesting patterns are. We're basically saying, I'm going to give you 32 channels or slots to find 32 chances to find interesting patterns. Okay, and again, I don't really know what size to make my window. So basically, I'm sliding a window over my first level convolution. So I'm convoluting a convolution here, I guess, and I don't know what size. So again, I'm kernel size 2 is kind of a small number. Basically, says it's going to look for lots of things. And we need a nonlinearity. We're going to use ReLU again, and then convolutions give us these sliding windows, which are going to look like 3-dimensional arrays. I need to get to outputs, one for each action. So I'm going to have to turn this into a more conventional linear for fully connected neural network. So I need to go from my convolutions to a fully connected layers, and this will basically be the third part of my neural network, and we'll say 256 neurons there. Just seems like a really useful number. We're basically shrinking now the neural network down. We're trying to reduce it down to the number of actions we have. And then finally, I need to make sure before I finish, I need to squish down to num actions. I've been talking about num actions. I don't actually know how many actions there are. Let's actually kind of figure that out. All right. What are our actions here? Well, it's a enumerated type. Okay, but that's good because I can actually ask how big this enumerated type is. So len actions, so there's 7 actions. Okay, so I actually knew that. The actions are something like turn left, turn right, move forward, toggle switches, pick up, put down, and some other stuff like that, which are kind of not interesting. But since we've got this up here, let's just make a new variable to remember that we have 7 actions. All right, and again, a nice thing to do here is just kind of make sure we have an output so we can actually see what that value is. So we can just look back here if we forget. Okay, so we're going to basically squish down to 7 outputs, right? So 7 outputs, they score the predicted score of every single action that is possible for the agent. And if we train this neural network right, one of these actions will have a higher score than the other, which basically is going to tell the agent what to do. Okay, so this is kind of what it needs to be in the neural network. We haven't written this. We're basically just writing ourselves notes. Yeah, and this is also going to be like my instructions now. This is like my notes about what I have to figure out how to make work. So let's actually kind of just like, I mean, I can run this here. It doesn't do anything, but let's actually figure out what the things are that should be in here. I'm going to, this is a little bit of a repeat, but I'm going to make sure I have a clean set of observations from my environment. So I'm going to reset the game, get my initial environment, and let's get that state. And let's go ahead and look at the state. Actually, what I really kind of care about is the size, right? So remind myself, all right, so it's 3 by 56 by 56. Oh, you know what? I just realized something. When we build neural networks like to do something called batching. Okay, so batching basically means that we could, if we wanted to, send multiple observations through our neural network or through the GPU simultaneously, which allows us to train more data in a single iteration faster. So this is called batching. To do batching, what you need, so basically what you're asking is like, I want to send, 3 or 5 or 10 or 100 different screens through my GPU. And my screen is a 3-dimensional array, right? So if I want to send multiple screens through, what I need is I need a stack of screens, which goes from a 3-dimensional array to a 4-dimensional array. So I should do that, right? So I should have a batching dimension here. So I'm going to come back up to prepare state, and I'm going to say I forgot to do that. What I should have done is, all right, so I'm in a tensor. They're floating points. I'm going to do something called an unsqueeze. Unsqueeze basically creates an extra dimension. And I'm going to rewrite that function. So if I come back down here again, now I have a 1 by 3 by 56 by 56. So I'm still going to do one batch at a time, but now basically I'm saying I have one set of 3 by 56 by 56 data. Okay, and we can actually look at this if we want to, right? We can look at what that looks like. Well, it's basically now just a 4-dimensional, but where the first element in the array is everything here, which is a screen. Okay, and again, 1 by 3 by 56 by 56. So this is a batch of one of what? One of these things here. So a stack of 3-dimensional screens. Okay, so that actually kind of was an important thing to do. And again, the nice thing is with the notebooks, we can always go back and change things and run things that we had there before. We don't have to run things in the order that we actually write them down. Okay, but let's go, actually, let's kind of get rid of this. It's still there, it still ran. I'm just not looking at the output anymore. Let's look up here. All right, so we need some convolutions, some relus, some max pools. So let's kind of look at every layer at a time. Let's try to make these layers. And I like to see sizes of things. So I'm just going to keep that on the screen here. All right, so if I want to make a convolution, I'm going to make a variable that holds a convolution. So you might think, well, shouldn't layers be inside neural networks? Well, they're just variables, right? They're objects, so we can make them anywhere I want. So I'm going to make them in a cell. All right, and to make a convolution, we actually want a conv 2D. And if we forget, Google Colab is nice enough to tell us what all the inputs and outputs are, right? If we're really not sure, we can go look at the instructions. Okay, so we need the number of input channels, the number of output channels, kernel size, and a whole bunch of other stuff that I'm not going to worry about here. But yeah, so what do we need? Input channels are 3. Why? Red, green, blue are our initial features. And remember, I thought we should have 16 channels coming out, so 16 features to be determined by the neural network through its learning process. And the kernel size we decided would be 2. Okay, so I can run this, and I've made a convolutional layer module. It's a little neural net. It's just sitting there in that variable conv1. Okay, so let's run some data through this, right? So I can take my state, and I can pass it right through this convolutional layer. And what we do is we just take that variable and we treat it like a function, and we say, give it this information. This basically runs the forward function on my conv2d and gives me some sort of output, which we'll call h1. H will just mean hidden, right? It's basically some intermediate piece of data inside what will eventually be our neural net, right? And so we can look at it. So I like to look at it, and I like to look at sizes of things. So let's go ahead and do that. Okay, and so what we have here is a whole bunch of random numbers. Why are these random? Well, we haven't trained anything yet. So it's basically spitting out random numbers here, right? And it's telling me that this was created by a convolution. So one of the important things about tensors is they remember how the tensors were created. They remember which module created them. And this will be important later when we actually train. And what comes out is a 1 by 16 by 55 by 55. All right, a batch of 1, because we're only doing batches of 1, but if we had more, we'd have more. Right, 16 channels or features, and 55 by 55. Okay, so the screens are 56 by 56, but we have kernel size 2, so we get a little bit of kind of compression along those 2 dimensions, just because we're chunking things in pairs of 2. Okay. All right, so we're now able to run our state, which was properly formed through our convolution, which we get some sort of intermediate state. Well, we always need a nonlinearity, which we decided was going to be ReLU. ReLU doesn't have any parameters, so we just kind of make one of those, and we can take the outputs of my convolution and run it through my ReLU and get a new hidden state. And we'll take a look at that too. Okay, actually, we're rerunning everything from scratch, right? We're running our state all the way back through both layers. Okay, so here was the convolution, right, which gives me a 1 by 16 by 55 by 55. Then we run it through a convolution. It's like it's giving me a whole bunch of zeros. Why is that? Rectified linear unit basically takes everything that's negative, turns it to 0, and then everything positive kind of comes out as is. Okay, so I'm getting a bunch of zeros and a bunch of positive numbers. Okay, and we're still at the same size, so ReLUs don't change the size. We still have the exact same number of neurons before and afterwards. And then what did I decide should come next? Convolution, ReLU, max pool, right? Okay. Let me see if I remember how to do a max pool. Let's call this MP1. It's going to be a max pool 2D, right? 2D dimensional information, kernel size, which we decided was 2. And we usually need something called a stride, which is basically how many steps should we skip. We're not going to skip any. We're going to stride over every single thing. So stride 1. So that does that. And we can take our hidden and pass it through our MP and see how that changes things. So again, we'll print it. All right. So here we go. We've got convolutional outputs, ReLU outputs, and my max pool. And we can see our max pool gives me an output of 1 by 16, batch of 1, 16 by 54 by 54. So again, the kernel size was 2. So we kind of, because of chunking and skipping, we kind of end up with a slightly smaller 3-dimensional array. Okay, so that is my first layer, basically is involving these 3 processes, the information flowing from through the state, through my ReLU, through my max pool, and we're here. Okay, so my second layer is another convolution and another ReLU, no max pool this time. So we kind of do the same thing, right? So conv2 equals conv2 2D. Now, what were my channels again? Right, well, this time we started about 16, right? So we have to have the same number of channels from our previous layer. And I think if I remember correctly, we were going to have 32, and we'll keep that kernel size at 2. Hopefully that will do us good. And that means we can now take our H1, our hidden layer, hidden information from the first layer, pass it through our conv2 get something else. And let's take a look at what this is going to look like. Again, we create this convolutional module. We run things through, we get a whole bunch of random numbers. Again, this module is untrained. And now here we have a batch of 1 at size 32. So now we have 32 features for the neural network to decide what's important. And again, our kernel size is causing a little bit of dimensionality reduction here on this level. But overall, we're getting more neurons, right? Now we have 32 of whatever these things are. All right, so we have our convolution, ReLU. So now pass this through ReLU 2 and see how things change. Okay. All right, again, we get lots of zeros, so we know this is ReLU. We expect that now, and ReLUs don't change the size. So we're all good there. So now we have our second layer. What was our third one? Now we need to go through some linear layers, some fully connected layers, because we want to get things down to 7 actions. Yeah, we're going to do this in 2 steps, right? So we're going to collapse everything down to 256 neurons, and then we're going to collapse it back down to 7. So this is an important pattern that we often do in neural networks. We make things bigger and bigger and bigger, which gives the neural network capacity to find features or channels, and then we squish it all down, which basically says, all right, start making compromises across all these features. You're going to have to compress things down and figure out how to, make use of smaller and smaller bottlenecks to make guesses. Okay, so we need to squish everything down to a linear layer, a linear row of neurons of size 256 neurons. All right, so let's get back down here to the bottom. So fully connected layers are called linears. So linear layers look like this, and you can see we have input features and output features. So we know we have to go to 256 output layers, but how many neurons are input? Well, I don't actually know, right? So this is a three-dimensional array. I need a one-dimensional array here. So I'm gonna have to do a little bit of work here. What I'm gonna have to do is I'm going to have to take, let's see, what came out of H2, and I'm going to have to take this three-dimensional array, 32 by 53 by 53, and turn it into one long skinny row of neurons. And the function we do that is with something called view, which basically takes an arbitrary tensor or array of any shape and puts it into any other shape, and just kind of remembers how everything moved from where it moved from one spot to another. So what I want to do is I want to basically have my batch layer here. So we don't want to mix across batches. We only have one batch, but basically we don't want to mix across batches. But everything else inside of a batch, those next three dimensions should be squished into one single one. So we're going to say there's one dimension here, and I don't know how big it's going to be. The -1 basically says, figure it out for me, figure out how many, what the size of this one dimension should be for me. And if we do that and run it, we can actually see now that this is collapsed down to a 1 by something. What is it? I don't know. Let's grab it as in a variable here, and let's print that, and more importantly, print the size of this reshaped tensor. All right, so here we go. It's a 1 by 898,888. Okay, so basically now we know we have, once we've reshaped this, squashed this into a single linear layer, we have 889,888 neurons, which we're going to now fully connect down to 256. Okay, so let's say we have an H3. We're going to pass our, not H2, but our reshaped H2 through our fully connected. And for sanity, let's print H3 and print H3 dot size, see whether we did this right. And all right, a whole bunch of random numbers, again, untrained modules. And we do see that whatever we had up here, which was 1 by 89,000, we now have 1 by 256. Okay, so we have successfully collapsed our tensor down. Okay, so we're all good there. Oh, right, we can't forget about the ReLU. We need a nonlinear activation function here. So let's make a new ReLU. Let's use that ReLU. And just to double check everything, because we're being very safe here, we see, yeah, we didn't do anything screwy. We have a ReLU coming into 1 by 256. Okay, great. So that is layer 3. And then the last thing we have to do is we have to take these 256 and collapse them down to our 7 scores. Okay, and now the top of our neural network is often called a head. So we'll call this the head. And again, we're going to take a linear function. We're going to take those 256 and we're going to go down to num actions, which was 7, right? So, and we will call these the scores, right? So the scores are what happens when we take hidden 3 and send it through our head. Just sounds weird. Let's make sure we did this right. And there we go. We have 1, 2, 3, 4, 5, 6, 7 numbers, 1 by 7. Yes, we did this correctly. I would actually, I'm not satisfied with this. You know, we have numbers that are negative and positive. That's because of just kind of the way the linear functions worked. What I would really like is numbers between 0 and 1. I'd kind of like to treat this as a probability. Like, what is the probability that action 1 is the best, or the probability that 2 is the best? We can do this with something called a softmax. So we will create a softmax layer. I don't think we actually have to. Just to be sure, we're going to tell it dimension 1, so stay away from that batching dimension, right? And what softmax will do is it will give us probabilities. Well, does it give us probabilities? Well, it normalizes everything in a tensor down to in a number between 0 and 1. But so we're going to basically pretend that this is a probability distribution across actions. So we're just going to take our scores, send it through soft, get p, and we're going to print p and print p.size. All right, we do that again. Okay, so now we have numbers. They're all kind of more or less the same. Again, our neural network isn't really trained to know any better, but we do have numbers that we can treat now as probabilities, and we have 7 of them. So the action that it thinks it should take is whichever one is going to have the highest probability, which looks like that one, right? So whatever that action is probably the one it probably should take. Okay. Great. So what have we done here? We verified the process of how we should transform our data from, if we go all the way back up here, from a state to a set of scores, or a probability set of over scores. But more importantly, what we've also done is, hold on one second. Okay, so sometimes you get calls from your parents while you're live coding something and recording yourself. All right, but importantly, we have kind of actually stepped ourselves through all the different transformations we want to do on the state. So if we want to now, and we know it's going to work because everything went through without error and it gave us the right shape at every single step. So now if we want to come back up here, just like we did with the prepare state function, we can start wrapping everything in our object. Okay, so then what do we just need to do is we just need to grab the modules that we created, copy those into our class definition. Of course, once we do that, we also need to make sure we define things within the class. So we're going to take the variables that were global and we're going to bind them within our constructor here. Okay, so that's step 1. Step 2, we grab the 2 modules that make up my second layer. Make sure they are scoped and defined within the object. Number 3. Where were we? There we are. Okay, those are the modules. Get those in there. And last one, the head. Okay. And our head ended up being 2 modules. Where are they? Here they are. Grab those. Yep, not using the GPU, I know. I haven't gotten that far yet. Patience, patience, computer. All right, so we got it there. One last thing, right? We need to make sure that we're using the num actions that was actually passed in here and not the global num actions. Okay, so hopefully if I didn't make any mistakes, we've got everything in our constructor. Now we need to fill out our forward function. And we also have done our forward function. These are all the transformations we did, right? So starting from all of our transformations on H1. Okay, so of course, it's not state anymore. We're passing in something called X. X is a batch of states. So we need to make sure we send X goes through H1. I guess we don't need all these print statements anymore. That'll get obnoxious really fast. All right, our 3 transformations for our first layer. 2 transformations for our second layer. Oops, here we are here. And we don't need our print statements again. Okay, so H1 goes to H1, H1 goes to H2, H2 to H2. Good there. Layer 3. Okay, 2 transformations for that. Of course, we do need to reshape that tensor, right? So let's grab that reshape. Kind of a little intermediate step we can't forget. Okay, so now we've got H2 gets reshaped, goes through H3. Yeah, and if we want to be really kind of robust, we will do not, because if we ever use more than one batch, we'll want to say get the batch size. Okay, so we can get the batch size like that. That'll just be a little bit more robust than hard coding the batch in. And our head. We get our scores, we convert them to the probability. All right. Okay, so H3 goes to our head, becomes scores, scores become our probability. We want to be really kind of straightforward. It is the probability is our prediction of the Y, the target values, and we're going to turn our Y hat. All right, so if we haven't made any transcription mistakes, we should be able to load this class definition into memory, and we should actually be able to build one of these things. So let's say our model is our net, and right, so our height and width and our num actions. And let's just take a look at this model. Once it's built, it works. Here are all of our convolutions, our ReLUs, and all of our other layers. Okay, great. So we've built this. Now let's make sure that it's actually working, meaning that we can actually send some data through. So I'm going to, I always reset the environment just so I know that we've got kind of a clean initial piece of data. We're going to prepare that. We're going to get into a tensor. And yes, let us predict the scores. So for that, we take our model and we pass our state through. And if this works, we should get something that, well, it shouldn't crash, which is going to, if I don't make any typos there. Y hat, and it should be of the size that we expect, which is a 1/7. So let's just do this whole thing from scratch, and boom, 1, 2, 3, 4, 5, 6, 7. We have a 1/7 output. These are the guesses for our scores. Awesome. So we look to be in good shape, but we're actually not quite done yet. There's actually something else I want to do. This is all running on the CPU, but we have a GPU, and neural networks are more efficient when they're trained on the GPU. So what I want to do now is I want to take my neural network and I want to move its data to the GPU's memory. Right now it's in CPU memory. And the way I do this is we're going, well, CUDA is the name of the API that gets data onto a graphical processing unit. So I'm going to basically tell it I want to move it through the CUDA API. which will take it to the GPU. So I'm going to rebuild my neural network and I'm going to move it to that. It's going to take a minute now because what it's actually doing is pushing everything in that neural network, all the parameters through the bus to the GPU. All right, there it is. Showed up there. And now my model isn't on the CPU anymore. It's on the GPU, which means I can't run it with information on the CPU. I have to take my data, my state, and I need to move it to the GPU as well. And I have made a mistake here. CUDA float tensor. So I have something. This is basically telling me that there's something that's trying to do something with something that's not on the network. So X, everything looks good here. Are there any layers that aren't inside the network? Oh, you know what I did? I made a big mistake here, right? I'm not using any of the modules that are inside the network. I'm using the global variable. So this is one of the problems of all the things that I like doing, this incremental debugging in the cells outside of the functions and outside of the neural network definitions. What happens is I end up with variables that are global with the same name as the variables inside of my object. So I was, in fact, calling the global modules that I had made during testing, which were not moved to the GPU. So it was catching this as basically saying, hey, you're trying to take something on the GPU, you're sending it through something that's not on the GPU. I was expecting all this on the GPU because I made a mistake here. So I'm going to basically make sure I'm using the correct variables, the scoped variables inside the object. Let's skip down here. Let's build a new network, get it on this GPU. And this time it works, right? So we moved our state to the GPU, pass that through, and we see here's a tensor output. That tensor is also on the GPU. And we can see that it was created by the last layer in our neural network, which was softmax, and it is of the size we expect. Okay, so now we know we can pass information through our neural network. So next thing to do is let's try to training this bugger, right? So let's prove that we can do some training. All right, so if we're going to train things, we need a couple things here. We need an optimizer. Now, PyTorch gives us lots of optimizers for training neural networks. One of them is called RMS-prop. That's the one I'm going to use here. Going to tell it what the parameters are that it will be optimizing, and sometimes you get a learning rate. I like to give a kind of some sort of learning rate. It's basically a small number that says always move the parameters just a little bit. This, and we need a way of measuring loss. And I'm going to use a loss function called cross entropy loss. Basically, what that does is it takes two vectors and basically tries to figure out how similar those vectors are. The difference will be the loss or the error. So in other words, how wrong did the neural network guess its y hat compared to the true value y? Okay, so I'm going to need these things. Let's go ahead and load these things into memory. What have we done? Model parameters. I just had a typo there, no big deal. All right, so that loaded in correctly. Now, if we're going to train something, we have to have loss. To have loss, we have to have the value that we want to compare against, a true value. The true value is usually called y, as compared to y hat, the guess of the true value. So I'm going to make up some data here. Basically, I'm going to train the neural network to move forward. And to do that, I'm going to set up 1, 2, 3, 4, 5, 6, 7. Is that 7? 1, 2, 3, 4, 5, 6, 7 values here. One score for every action. Okay, and what I'm saying is the third action in index 2 should be, I'll get as close to a value of 1, a score of 1, and everything else should have a score value of 0. Why am I doing that? Well, because this is the forward action here. So we can actually see this. We can go to environment actions forward, and it is the second element in that enumerated type. Okay, 0, 1, 2. So we're going to train the neural network that the correct action to do is 1. So this basically says my true score that my neural network should guess based on its input is some numbers close to 0 and some number that's close to 1 and some more numbers that's close to 0. Now we'll never get down to true zeros and true ones, but we're going to say get as close to this actual value as you can. And since we're doing everything on the GPU now, we better move that to the GPU. And let's go ahead and print. Let's just take a look at y, make sure we did that right. Okay, so 0, 0, 0, 0, 1. Yep, okay, great. All right, and so the loss again is the difference between y and y hat, as determined by my criterion, which I set up earlier. I give it my estimate, the output of my neural network, and I give it the true target. And then let's just kind of see what loss we get here. And that's going to blow up. Why did that blow up? All right, expected floating points for target got longs, right? See here, what we did is we used zeros and ones, which is interpreted as longs. So there's a couple different ways we can do this. We can tell it to use the float values. And now we have floating point values, and we do in fact get a loss here. There's another way we could do this. We could actually do an explicit typecast here. We could do it like that, and that'll also work. Same value, same output. Okay, so now we can compute the loss. And basically this is saying how wrong was y hat the guess based on what we told it that we wanted to see. Okay, once we have loss, we can do back propagation, which trains the weights. What we're going to do is we're going to tell it, make the parameters, and we can't see any of these parameters. They're all hidden inside these modules, but there's a whole bunch of parameters inside this neural network when we set up all these modules. We're going to say, change those parameters so that if you see this observation again, you get a little bit closer to the 7 values that we actually expect to see. So there's 3 things we want to do here. We're going to take the optimizer. We're going to do something called zero grad, which basically says zero out all the gradients, basically do a clean, fresh run of the back propagation optimizer. We're going to call backward, and I'll come back to what we do here, but that basically runs back propagation. And then we're going to tell the optimizer that we're done, that we've completed one of its steps. Now, a little bit of this is one of the most confusing things in PyTorch. What is loss.backwards? Well, we're calling the backwards function on the loss tensor. This is the loss tensor here. So if you remember, it is a tensor that holds a single value, a scalar. It's on the GPU, but more importantly, it was created in a particular way. The last operation that created this was a division, but that division is something that was happening inside the criterion, which was the implementation of cross entropy loss. The cross entropy loss received y hat and y. And of course, y hat was this tensor, which was created by the softmax, which was created by some matrix multiplication, an add and multiply, which was created by a ReLU, which was created by some more matrix multiplication, and so on and so forth. So basically what has happened is that if we go back to our neural network, when we ran our state, our X, through this sequence, every one of these intermediate tensors remembered how it was made, remembered who made it, and each one of these modules knows how to do back propagation on its parameters. So by calling telling loss to compute backpropagate on itself, we trigger this recursive backpropagation where loss says, all right, I'm going to perform backpropagation on the person who created me. And that's going to cause a backpropagation on the module that created the intermediate tensor that came before it, and then so on and so on until it gets all the way back to the beginning of the whole set of transformations. So this is all you really need to do to create this cascading backpropagation. And once you do this, the network starts to learn to get the loss closer and closer to zero. Okay, so we can run it just to prove that it works. And so yes, everything works. The backpropagation succeeded. Now, if we really kind of want to see what's going on in here, sometimes I do this just to prove that my neural network is actually learning something. I can actually go and look at those parameters. Something we haven't done yet, but basically I can go into my model and I can look at all the different parameters at all the different layers and all the different modules. So print parameter I, and then I'll actually print the param. All right, so here we are. These are all the different layers and modules we have going. All right, so the first parameter is from our first convolutional network. So this is all the different parameters. There's some other parameters. Here's our second convolution. These look like to be our linear layers. Here's the big one from 89,000 to 256, or 256 to 7. And our, yeah, right. So there we are. Those are all the steps going on here. All the hidden parameters, all the weights. We're basically looking at all the weights, right, that changed. And then what I want to do is I want to prove that when we do a backpropagation, that these parameters actually change. So let me do this. I'm going to move this up here. Let me build a new neural network from scratch. Okay, just make sure we've got everything clean. All right, new model, new input state passed through our model, giving us some values here. Okay, make sure our optimizer is set up, compute our loss. Let's go ahead and look at these parameters again. All right, so our first parameter has some weights like 2557. Let's just remember that one. We do some back propagation through here. And if I come back up here and run this again and look at my parameters again, 2556. Okay, so this number went down a little bit. That means our parameters are changing. Our weights are changing, which means back propagation has actually successfully used the loss information to adjust some of the weights. And so if we keep doing this, keep sending input states screens through our neural network and getting outputs and comparing them to some sort of target, this will eventually get our weights closer and closer and closer, and we should hopefully get some sort of loss that goes closer and closer to zero. And maybe we can actually see this. Let's get another observation. We're actually getting the exact same initial observation. And yeah, we went from 1.9 to 1.6. So it's actually learning, right? Loss went down a single step. Now that's one screen, and we've backpropagated on one screen, which we shouldn't actually do. But we can verify that the system, the model, the neural network, that can actually learn. And that's great. Okay. If we're kind of curious, we can ask what action did it actually score highest? That's y hat, right? We can take a look at that. Well, that's, I'm not exactly sure what. Here's what we do. What we actually care about is which is the action that has the highest score. So we'll argmax across those 7 values and action 2. So this is kind of good. Well, I mean, not good. This is 2 is forward, so we can actually see this execute. So let me print y hat, and then we'll get the action, and the action again is y hat dot argmax along that dimension. And we can print that action just for our own sanity. right? We know it's action 2, and we can actually send that back to the environment and say, go ahead and execute that action. And if we do that, it'll give us some pieces of information. It'll give us a new observation. It will give us some reward, which might be 0. It'll tell us if the game has ended, and there's this additional piece of information that is kind of for future use that's not being used right now. So we just capture that and put it into an empty variable. Okay, so if we actually do that, we can actually execute that action. And if we want to verify that that action was successfully executed, we can come back up here and we can ask the environment to render itself again. Show me what the environment looks like now. And we see that the agent has moved 1 step forward. So this also means that we can take the outputs of the neural network and we can feed it back into the environment, which is going to be important if we want to run the agent or do some sort of deep reinforcement learning or something like that. And then we can also look at what this new observation is, right? What is the agent seeing now that we've executed this step? We'll just verify that something interesting is happening here and is correct. So our new observation is this, right? So it is 1, 2, 3, 4 steps away. So it now sees the wall 4 steps away. Again, egocentrically, it's looking forward from this intermediate spot here. So it doesn't look too different, but it is. Okay, so that kind of proves that I have a full end-to-end loop of data going into my neural network. Through my neural network is able to learn from the data and the way we compute the loss, and that we can take the outputs, figure out the right action, and feed it back into the environment. So at this point, we basically have proven that we have a full end-to-end loop. Now, if I wanted to make this into a training loop, I would have to kind of wrap all these steps inside some sort of training loop, which I'm not going to do that right now because I just wanted to focus on the neural network. But again, the whole point of this was to show that we could kind of iteratively build out this neural network step by step by using the notebook environment itself as a debugging tool to basically make sure every single step is done the correct way, so that when I put everything together, I know that this thing is going to work, and I don't have to kind of deal with trying to run, fix, run, fix, run, fix, right? I did all the running and fixing kind of in these little intermediate cells, and I'm done with these, right? So I can actually kind of even delete these out and keep the stuff that I need to keep. Okay, so again, not teaching you how neural networks work, but just kind of give you kind of some guidance on how to build incrementally neural networks that are going to work and debug as you go using the feedback that these notebooks give you. And with that, I am out.